Alright, let's slay this monster of a question. So we'll start off with this series, name it S1, and remember this is a Sin X power series. We can see that they sort of look similar. So we'll rewrite the series, and we'll see that this has to equal this if we want it to equal this. So looks like a power rule, so we'll let y equal tan of x. So yep, replace these and rewrite it. Then we'll integrate. So yeah, bring the integral into the series, and there, these two cancel out, and now we're left with this, which is similar to that. So this series equals sine of y. So what does the original series equal to? Well, if the integral of the original series is equal to sine of y, then we could just take the derivative of both sides, and boom, we get cosine of y. If y equals tangent of x, then that means the answer is cosine tangent of x. So, yep, we'll continue. So our original question, we're going to be focusing on that element. So now we know that it simplifies to this. We'll call that I1. So let's separate the numerator and denominator, and we'll notice that these two are here, which is sus, because if you recall that 1 over cosine squared of x is equal to secant squared of x, and that we'll rewrite into the integral like that, and this just looks prime for u substitution. So we'll set it up with u equals tangent of x, and we'll isolate for dx, and we'll find that it simplifies to just cosine of u du. So the answer is sine of u plus c, or sine of tangent of x. Super. Now our original question simplifies to this. So we'll focus on this limit first, right over here. I mean, looks pretty easy, so let's get into it. This, we'll do the derivative first. So it looks pretty easy. We'll just do quotient rule, easy clap, there's our derivative, and now we plug it back into the limit. So here, when we plug in x equals infinity, we get infinity over infinity. So,
oh, here we go.
You know what that means. L'Hopital's rule.
We
just take the derivative of the numerator and denominator. Then we'll do some simplifying, and we'll find that it equals to 0. So that means our limit over here is just equal to 1. So here's our original question simplified. So we plug x equals 1. So that's sine of tan of 1, which is sine of pi over 2, which we know is just 1. Ooh, we're getting close. Now we have this. So we'll focus on the integral. And yeah, so here's our integral. Factoring time, which everyone hates. So first we'll do GCF in the numerator, and then factor out using a simple trinomial method in the denominator. And now our integral is ready for partial fractions. So we want it to look like that. So we'll get the integrands, set them equal, and solve for a and b. So letting x equal -3, we get b equals 1/4. And letting x equal 5, we get a equals 3/4. So now we solve for both a and b. we'll sub it back in, pull out the constants, and get the antiderivative. And then now we do some calculator work. We get 2.874. Interesting. So our integral is, so we multiply the answer by 8 and we get 22.99. Interesting.
Yeah, boy. Yeah, boy. Yeah, boy. Yeah, boy.
So we have our series here, and if you remember from Algebra 2, we'll evaluate that, and we get 68.97. Okay, that's nice. But wait, we have to remember we have to round the answer to the nearest whole number.
Ladies and gentlemen,
It's the funny number.
we got him.